Hello, and welcome to the Chapter 17.1 lecture on vector fields. A vector field is a function that assigns to each point x, y a vector. And vector fields occur everywhere in nature. So for example, wind currents, we can think of that as a vector field. At each point, we have a direction and magnitude of the wind current. Or a magnetic field, at each point, we have a direction and magnitude of the force. So this is the formal definition of a vector field. We typically denote it with a bold F, and that vector field F assigns to each point x, y a vector at that point. And a vector field is continuous or differentiable on a region if its components are continuous or differentiable. Here is an example of a vector field. This is F is 2x, 2y. As you can see, if x and y get bigger, then both components get bigger, and so does F, and that's illustrated here. As x and y are bigger, then the magnitude is bigger. And this vector field is always pointing away from the origin. We can sketch vector fields. Let's sketch the vector field negative y, x. So at each point, we plug it into negative y, x. So plugging in some points into this, just as an example, we can see that if we plug in 0, 0, we get 0. If we plug in 1, 0, we get 0, 1. Let's graph that. 0, 1 looks like that. At 0, 1, our vector is negative 1, 0. There it is. Here it's 0, minus 1, etc. At 1, 1, plugging in, we have negative 1, 1. Okay, there is negative 1, 1. Here we have minus 1, minus 1. At 2, minus 3, we have 3, 2, etc. So at each point, we have a different vector. We can't really see what this vector field looks like on a large scale from this, but let's plug it into a vector field graphing program. The vector field looks like this. So this is the vector field negative y, x. We plotted some of these points, and you can see that overall, it looks like this vector field is swirling around the origin counterclockwise, and the magnitude of the vectors are getting larger as x and y get larger. So that's graphing vector fields. With some experience, we can get a feel for what these kinds of things look like mentally. We can also have vector fields in 3 dimensions, and all that means is it assigns to each point in 3 dimensions a vector. So for example, the vector field xy, e to the minus c, getting a feel for that mentally, what we can do is we can take traces, just as we have done a lot in this class. Take the horizontal trace, which would mean don't consider the z component for the time being. It's x, y. We already saw what that looks like. X, y, it was that vector field is always facing away from the origin. And then the z component, e to the negative z, that guy is approaching 0 as z gets bigger and bigger, so it will be flattening out. And that's exactly what this is. It's always facing away from the origin horizontally, and it's getting less and less steep as z gets bigger. Now, a very special type of vector field is a gradient field. A gradient field is exactly what it sounds like. We learned what a gradient is. We learned what a gradient is in chapter 15, and a gradient is a vector, and given a function, every point has a gradient there. So any function that's differentiable generates a gradient field, just the field of the gradient vectors. And remember that the gradient always points in the direction of steepest slope. The function that gives the gradient vector field is called the potential function. So these would be the level curves of the potential function, and the gradient of that potential function is the gradient field. And so in practice, the potential function will often be in physical applications the potential energy, and the gradient then would point in the direction of steepest increase in potential energy, but things move in the direction of decrease in potential energy. And that's why in physics, often the gradient field is negative grad of phi, to make it so that the gradient faces downward, corresponding to things decreasing their potential energy. And we define a conservative vector field to be a vector field that arises as the gradient of some function. These are very important, and we'll be talking a lot more about them. Following the gradient vector field generates flow curves, as we call them. They are the direction that water would flow. If this were a mountain or hill, it always flows in the direction of steepest downward slope, and that is given by the negative gradient, at least in the physical application. And directions orthogonal to the gradient vector field are called equipotential curves because they are the level curves, and if this is a potential energy function, then they are curves that maintain the potential energy. So just to brush up on gradients and give an example of a gradient vector field, literally any function of xy generates a gradient field so long as it's differentiable, given by the gradient. It's that simple. So here f would be the gradient of this, which is the two respective partial derivatives, which is this. So that's a gradient vector field. That's all there is to this very short introductory chapter. Have a good one.